Hello everyone, my name is Andreas Lehmann. I'm from the GEOMA Helmholtz Center for Ocean Research in Kiel, and I will talk today about climate change in the Baltic Sea area, an inventory over the recent 40 years. And this is a contribution to the EUKI project, the European Climate Protection Initiative, and we will talk about the Baltic Sea. First, we will get a little bit familiar with the Baltic Sea, and so we need to know some characteristics of the Baltic Sea, which you can see here on this side. We see an empty Baltic Sea, so all the water has been evaporated or has lost, and then we see the bottom topography. And just for the orientation, Kiel is here. This is the island Fehmarn, Langeland. Here's the island Rügen, Bornholm, Gotland Basin, the island Gotland, and here the Åland Sea. Here is St. Petersburg, Helsinki, and Stockholm. And here is Gdansk in the Bay of Gdansk. So what is obvious is that we have a very shallow area in the connection from the Skagerrak, this here, to the Kattegat into the Western Baltic Sea. And we see here we have some channels. These are the connections between the Kattegat and the Western Baltic Sea. And these shallows are very narrow and also very shallow. And they restrict the water mass exchange from the North Sea to the Baltic Sea, but also the other way around from the Baltic to the North Sea. And then we see that there are some areas where it gets a little bit deeper. In the Arkona Basin, here we are around 40 meters, and then we come to the Bornholm Basin around 100 meters, and we can go further into the Eastern Gotland Basin. Here it's around 250 meters, and then it's getting shallow in the northern parts again. Some numbers: the areas are 412,560 kilometers squared. We have a volume of 21,631 cubic kilometer. The north-south extension is from 54 north to 66 north, and an east-west extension from 10 degrees to 30 degrees, and that's around 1,000 kilometers. The mean depth is only 52 meters, and so this is important when we compare the Baltic Sea mean depth with the Atlantic, for example, that we have something like 4,000 meter water depth, and here we have 52 meters. And that's rather shallow, and that means that the Baltic Sea is strongly affected by the wind, which is blowing over the sea. We have a maximum depth of 459 meters, and that is in the Landsohr Deep, and that's here in this area, but that has in principle no meaning for the Baltic Sea and also for the Baltic Sea dynamics. Then what is also important is the circulation of the water masses in the Baltic Sea, and on this sketch we see again the coastline. Here's again Fehmarn, here's the island Rügen, Bornholm, Gotland. Here it's going again to St. Petersburg, Helsinki is somewhere over here, and Stockholm is somewhere there. And we see here two kind of arrows, some which are green with a green color and some of the red color. And the green demonstrates the circulation of the surface circulation, which means this is also connected to low salinity, to low values of salinity. For instance, we have in the Baltic Sea a mean salinity between 6 and 7 gram per kilogram. In the Atlantic and also in the North Sea we have 35 gram per kilogram salinity. So this is a so-called brackish water body with low saline water, and we can see that there are some circulations happening in the different basins. And then the interesting part is the red one, the red arrows, and these transport high saline water, high salinity water. And this high salinity water has a larger density compared to low saline water, and that means it sinks down to the bottom like cold air in a room or something like that, and then it spreads from this part along the bottom topography into the central Baltic Sea. So one way is when we come from the Kattegat here in over the Great Belt and Fehmarn Belt further into the western Baltic Sea, then it passes the so-called Darst Sill and sinks to the bottom into the Arkona Basin. And there's another way through the Öre Sound. It also sinks to the Arkona Basin because of the higher density. And from there it can spread along the Bornholm Gut into the Bornholm Basin, and from there to the Gotland Basin, which can be seen on these arrows here. So we have a movement of surface water with this circulation going outside of the Baltic Sea into the Kattegat, and an inflow of higher saline water, mostly following the bottom topography. An important number is the river runoff. It's about 450 or 470 cubic kilometer per year, and that is rather a huge number. It's comparable with the river Mississippi, one of the largest rivers in the world. So that means there's a lot of water, of river runoff coming into the Baltic Sea, which reduces on the one hand the salinity in the surface water, but all this water also has to leave the Baltic Sea, so we have on average an outflow out of the Baltic Sea. Okay, so the effect of this large river runoff on the salinity can be seen on these two slides here. We have here a horizontal map which shows the monthly mean salinity for October 2018. Again, we have the coastline of the Baltic Sea, St. Petersburg again here, Gotland, Bornholm, Fehmarn and Rügen and so on. Here is the Skagerrak, this is the Kattegat, and then here there are the central parts of the Baltic Sea. And it's interesting to see that the Baltic Sea has more or less only these blue colors, which means the salinity is strongly reduced. It's between 10 or even less until 5 or 0 PSU or gram per kilogram. So if we go to the most eastern part of the Baltic Sea to St. Petersburg, there the salinity is more or less 0. And if you go to the very northern part, then the salinity is also close to 0. In the central part, the salinity is something between 6 and 7 PSU, and it's then getting stronger, more haline if we come to the Kattegat, to the Skagerrak and to the North Sea, where the salinity is 35 PSU. So here we have an area where the Kattegat water masses and the Baltic Sea water masses meet each other, and that is a so-called frontal region for salinity. If we look at the section through the Baltic Sea, which is seen here on the right side, this means we're going with a ship coming from the Kattegat, going through the Great Belt, Fehmarn Belt, over the Darst Sill into the Arkona Basin, Bornholm Basin, following then over the eastern Gotland Basin into the Gulf of Finland. And that can be seen on this slide. This is the depth and that is the distance. And we see here the red colors, again the same salinity colors, where we have the high salinity water from the Skagerrak Kattegat. And then we have the very low values in the Baltic Sea, where we have these brackish water masses where the salinity is strongly reduced between 6 to 7 PSU. And we see a strong stratification of salinity in the deeper part of the Baltic Sea. And this is water which has entered the Baltic Sea over the pathway which we just discussed before. Okay. Then there's another parameter, this is oxygen, which is rather problematic for the Baltic Sea, and this is also very important for the marine life. And we see on the left-hand side the frequency of oxygen deficiency of areas where we have permanently oxygen deficiencies or where the oxygen deficiency is varying. And we can see this directly from this graph, that in the eastern Gotland Basin and also in the western Gotland basins, the oxygen is always missing, and we have a high 100% oxygen deficiency in these areas. In other areas we see in the northern part of the Baltic Sea, this is more or less white. This means we do not have hypoxic or anoxic conditions, and that is similar also in the Gulf of Finland. The conditions are much better. But in the deep part of the central Baltic Sea we have some problems. We see this also in the Bornholm Basin, and also in our region it's getting more and more problematic. So it's now around 30 or 20% frequency of oxygen deficiency. So that is increasing also due to the climate change. And again, the section, now we look at oxygen, again the depth and the distance, and we see here these in the central Baltic Sea, again these red part where there is no oxygen or where we have the hypoxic oxygen conditions. In the deeper part of the Gotland Basin, that means all over the years the oxygen conditions are really worse in this area. Okay. Then we have to look a little bit outside of the Baltic Sea to understand also the climate change which is happening in the Baltic Sea. And this slide has been taken from the website Vent2Sky, which shows the results from a weather or climate model. And we see here the North Atlantic. Here's America, Newfoundland, Nova Scotia. This is Greenland, Iceland, the British Islands, and then here this is the whole part of the Baltic Sea we are interested in. And we see these two structures in the air pressure, and that's one with this T mark, that's a low pressure system which is called the Iceland Low, and we have an H for a high pressure system which is devoted or connected to the Azores Islands. So the important thing is that these are large-scale atmospheric patterns which exist more or less all the year in a little bit different structure. They are moving a bit and they are getting stronger and less stronger. But the important thing what we can see here is that we have a high pressure or a pressure difference between the Azores High and the Iceland Deep. And we see that this strong pressure gradient is also connected to wind, and that means if these two systems control the wind and the weather which is happening in our Baltic Sea area or in Northern Europe. And that's important to notice because these are not permanently at the same position, they move, and as I said before, they are getting more stronger and more weaker, and that influences the whole weather development over the Baltic Sea, and of course also on climate scales. Good, now we look into a number of parameters which are changing due to climate change, and the first one, which is always prominent, is the sea level, and we look here in the trend of the absolute sea level on this slide. Here again is the Baltic Sea, and we can see that there's more or less the same trend in the absolute sea level. It's around 2 to 3 millimeter per year. And this is more or less the same, but we also have outside the Baltic Sea on the global scale, it's more or less the same increasing sea level. But in the Baltic Sea, we had for 10,000 years, we had a strong ice development, and so we have to notice that there is some sort of land uplift in the northern parts of the Baltic Sea, which we can see here. And in other areas where we have something like a downgrading of the coastline, where then the increase of the mean sea level and these up and down lift compensate in some places, but in other places they are just adding each other. So that could be a problem. So we then need to look at the trend in relative sea level, and this is different in the different areas of the Baltic Sea, as we can see here. In this northern part, it's between 4 to 3 millimeter per year, and here we have it also 2 to 3 millimeter. But it's a bit different because of the different directions of the land uplift and downgrading. So then if we look at the total sea level change along the coast of the Baltic Sea, we need to look at a number of external and internal parameters. So we have already discussed the global sea level change, which comes from the thermal expansion of the seawater and also the melting of the glacier and from the glacial ice shift. So all the ice which is melting from the land somehow comes into the ocean and of course increases the sea level. We have also the inflow from the North Sea, which plays a role, river runoff to the Baltic Sea, storm surges reaching from outside over the North Sea into the Baltic Sea, and tides play a role. Internal, we have SAGE, that is the eigenoscillation of the Baltic Sea, wind waves, wind stow, ocean dynamics, changes of density, currents and circulation, and land uplift and subsidence. So all these need to be considered, because all these different parameters can, at the worst case, just add to each other, and then we get some extreme water levels, maybe which can happen then under these climate change conditions. Another parameter is sea ice. We see that the sea ice, here's a figure where we look at the sea ice extent from 1979 to 2018. You can see this here. Here is the time, and there's the areal extent of sea ice. We see that we have a high fluctuation of the sea ice conditions over these years. But we see in general that there's a decreasing trend of the sea ice extent in the Baltic Sea. And if we look at here on these slides on top, we see this is the conditions where we have a mild winter. That means only the northern part and very few parts of the eastern part are covered by ice. And if we have a strong winter, then the complete northern part and also the Gulf of Finland and the Gulf of Riga and parts of the central Baltic Sea are ice covered. This happened last time in 1987. And if we look at the very mild winter, this I guess is from we have on the next slide, we go here, we have the ice chart from the end of or middle of February in 2020. So last year we see only in the northern part there's some sea ice left, and also a little bit close to St. Petersburg, and all the other areas ice free. And this time of the year, so in the middle or end of February, is the maximum ice coverage. So that means there was nothing happening with more ice coverage. So this is more or less the maximum ice extent, and this is very, very little compared what we have before. Okay, then we will look now into a comparison of the Kiel Bight and the Gdansk Bight. So two positions in the Baltic Sea, more or less at the same latitude. We see here and that has measurements from the Kiel Lighthouse, and at the Gdansk Deep, this is here in the Gdansk Bay. And so this is one part more or less in the central Baltic Sea, and here it's more in these Danish Straits, so in the beginning of the Baltic Sea or entrance of the Baltic Sea. And we look at different parameters, start with the air temperature at Kiel Bight, this is from the lighthouse data, and for comparison the Gdansk Bay. We see the temperature, and here's the time axis. Again, we see this fluctuating in the air temperature, and that is due to the seasonal variability. And what we can also see is that we can detect warm summers where we have these extreme values, and also mild or cold winters can also be detected if we look at the minima in the air temperature. In total, the difference from the beginning of this time series to the end is 1.9 centigrades. So that means the air temperature over the Baltic Sea have already been warmed up for 2 degrees over this 40 years period. And this is interesting because we have from these Paris climate conference or something like that, there was the attempt to do not increase the global air temperature to 2 degrees, to 1.5 degrees, and we have now for the last 40 years we have already 1.9 degrees reached for the area of the Kiel Bight in this area. If we look at the temperature at Gdansk Bay, we see that there's similar behavior with these minima and maxima and the strong fluctuation because of the annual cycle. And we see that here the difference in temperature is something like 2.1 degree, so even higher than in the Kiel Bight. We can look at the precipitation over this period. That can be seen here, precipitation, annual precipitation in millimeters. And again, the time axis, we see that we have a high fluctuation, but the change is rather low. It's only minus 3.2 millimeter per year, which is changing between the beginning and the end of the time series. And in the Gdansk Bay, well, there we have a minus 1.7 millimeters, so it's even less compared to the keel bight. So if we look at the wind velocity, then we see again very strong fluctuations. Of course, there are years where we do have quite high wind velocities, but there is not really a trend visible, and it's also not a positive trend. At best, it's something like a negative trend. So that means the wind velocity is somehow decreasing of minus 0.5 meter per second. And for the Gdansk Bay, we have a similar structure. Again, these high fluctuations, and the wind velocity is decreasing by minus 0.7 meter per second. And the wind direction, if we also calculate this kind of trend line, you see there is more or less no change. On average, we have something like a southwesterly winds with a few meters per second over the western Baltic Sea. Then if we go now into the Baltic Sea, we can look at the salinity. This is now a figure where we have the depth axis here on the y-axis, and this is the time. Again, starting from 1979, going to 2018. And we see here in these colors the salinity. The blue colors means low salinity, and the red colors means higher salinity. And again, over the same period, we can detect something like the salinity difference is minus 0.5 gram per kilogram in the surface, and in the deeper part it's only 0.1 gram per kilogram. So an increase in the deeper parts and a decrease in the upper part is found for salinity. If we look at the temperature, then again we have also in the water the strong seasonal variability. We can detect the increasing or decreasing surface temperatures, and the same for the deep water temperatures. We see the difference we start from 1979 to 2018. At the surface is 1.8 centigrades. In the deep it's 1.1 centigrades. So it's similar what we have from the atmospheric temperature, and that is quite nice. So that the air temperature, the increase in the or the warming of the temperature is also apparent in the water in the Baltic Sea. And if we look at oxygen, that is in the lower panel, we see also the seasonal fluctuation there. That's due to that the solubility of oxygen depends on the temperature. So if it's cold, then there's more oxygen dissolved. If it's warmer, then there's less oxygen dissolved. So that means it's just the counterpart of the temperature. So in high temperatures, we have low oxygen conditions, and in low temperatures, we have high oxygen conditions. And we have a difference from minus 0.3 milliliter per liter at the surface and minus 1.2 milliliter per liter in the bottom layer in these key lighthouse data. So that is mainly due to this effect due to the warming of the water. In the Bay of Gdansk, it looks a bit different, especially for the salinity. We do have some long period signal of salinity, and that is the water which has entered the Baltic Sea through the Kattegat and the Great Belt over the Arkona Basin, Bornholm Basin, and so on, ending in the Bay of Gdansk. And that has taken quite a lot of time. Again, differences are minus 0.7 at the surface and plus 0.4 gram per kilogram in the lower layer. So the same what we also experience in the keel station, that we have a reduction of salinity at the surface and increase in the lower layer. For temperature, we have again a similar signal. We have an increase of 1.9 centigrade at the surface and 1.7 centigrades in the deeper layers. For the oxygen, it's even more problematic, minus 0.3 milliliter per liter at the surface and minus 0.9 milliliter per liter in the bottom area. And what we can also see is that we have more and more getting these blue colors in the deep part of the Gdansk deep, and that means that the oxygen conditions getting worse and worse in this area. Okay, just to summarize, we have looked at a number of parameters, and We will now go through them. We have looked at the sea level. So the global sea level rise is also evident in the Baltic Sea and has similar values than compared to the global sea level rise. We get 1.4 millimeter per year in the period from 1979 to 1990, and it's increasing to 3.3 millimeter per year in the period from 1993 to 2018, which means we have an increasing trend of the sea level rise, and all in all, for over these 40 years, we have an absolute increase of 10 centimeters. That's quite a number. But this is not all. So if we look at the local sea level changes, we have to take into account a number of other parameters, like the mean sea level, which means also the filling of the Baltic Sea, in and outflow conditions, the wind star, wind waves, seiches, swell, and tides. All this needs to be considered, because in the worst case, all these components can overlay each other, and that means we can get very extreme water levels at the coast. The temperature, or the air temperature over the Baltic Sea, is increasing. We had about 2 degrees over the recent 40 years, and the water temperatures just follow these signals. We see also that the oxygen solubility is reduced, and also due to the warming, the oxygen depletion is increasing because of biogeochemical processes which play a role and which lead to oxygen deficiencies, and all this because also we have a very high level of eutrophication in the Baltic Sea all the time. Even so, there has been some improvements, but it's still very high. So that means the high eutrophication and the warming strongly reduces the oxygen conditions, and that has a negative impact on the recruitment of commercial fish species like cod, herring, and spread, and the corresponding habitats. In the salinity, we have seen that it's at the surface, it's slightly decreasing, whereas in the deep water, the salinity is increasing. This leads to stronger stratification, reduced vertical exchange and mixing, and even enhances problems with oxygen in the deep layers. Just some slide here, just showing our fish and what is happening due to the global warming and the eutrophication process. This acts on the changing habitats, on the habitats of the fish. We have here cod, and here are the clupeids, it's herring and spread. And that means this changing habitat has an impact on the oxygen conditions in the deep basins, and it can happen that hypoxic areas can quickly extend, and that will lead to dying of the fish and also of problems with the recruitment. There are also hypotheses like match and mismatch for specific fish species. That means the recruitment or the spawning and the egg development is somehow out of order because of changing temperatures. And we have also an introduction of invasive species, which sometimes also doing harm to the local fish species. Okay, then the last point, the eutrophication is still an issue. It's getting worse even under the problems of the climate warming. And the eutrophication also leads to cyanobacteria blooms, and of course this extension of hypoxic areas. For the ocean acidification, it's so that we have increasing CO2 concentrations, but the acidification of the Baltic seawater, we do not see a really trend that this is increasing. The reason for this is unclear. It seems so that there are some insufficient measurement methodologies, or increasing alkalinity might be the reason. Yes, and then the last point is the weather lab of the North Atlantic, which is controlling the weather development over the Baltic Sea and also over Northern Europe. And it's important to notice what has happened with these North Atlantic weather lab also during the climate change conditions. So we get some milder winters, which can be seen in this weather lab, and also other things like stronger winds or changes in the circulation are important. So that means to understand the climate changing in the Baltic Sea, it's necessary to look at the North Atlantic large-scale atmospheric patterns. Okay, thank you. That's all, and